Good morning, everyone, and welcome back to Computer Systems. Today we're going to talk a little bit more about one of the major themes for this semester, and that is concurrency, parallelism, and how those things cause us horrible problems that then we're going to have to spend a bunch of effort trying to fix. So, specifically, we have this problem where modern computers are parallel. And what that means is you can't buy a single core machine anymore. We haven't been able to buy a single core machine for like a decade. So that means that if you want to write a computer program and you want to have it be as fast as possible, you want to have it take advantage of the computer resources that are available, you're going to have to either have multiple processes, the way we've seen with fork, or we're going to have have multiple threads. Those threads are going to have to run in parallel on multiple CPU cores. That's great. We know how to do that, and there's a bunch of techniques that we can use to make that work out. But as soon as we have multiple threads, we start to run into the problem of data races. And now data races require three things in order to make them possible at all. Now, think for a second. Do you remember what the three things are? You should at this point. If we had exams, this would definitely be on the exam. In fact, this might be the whole exam, is just remembering these three conditions for a data race. So here they are. First, we have to have concurrent/parallel execution. And really just concurrent execution. Second, we have to have shared data. So between the two processes or threads running concurrently, or more than two processes and threads running concurrently, they have to both have access to the same object in memory. And then at least one of those accesses to the shared data has to be a write, and that implies that the shared data must be mutable. So frequently when you hear people talking about this problem, they'll talk about mutable shared state as being the problem, sort of implying that obviously we're going to have multiple threads in a modern computer program. Now we've looked at how to solve this problem. One solution that we have for this problem is using a mutex, and that raises the issue of deadlock. We have some other patterns that we saw. The barrier pattern, if used carefully, allows us to solve this sort of problem, but that requires us to think real carefully about what we're doing. We have semaphores, which let us do some tricky stuff, like that shared queue example that we looked at with two semaphores and atomic operations. And we can just use atomic operations directly. But all of these are sort of fiddly solutions to the problem and require a lot of work on the part of the programmer to make sure that the program is correct. Because if you mess up a little bit, the program is no longer correct, you didn't actually solve the data race, and you're back to programs that randomly corrupt their memory, and so at best they produce wrong answers, and at worst they corrupt all your data and punch your dog. So we don't want any dog punching in our computer programs. So the thing that I want to look at today is solutions not in C. How do other programming languages provide especially higher level solutions to this problem? And before we get into that, I want to talk a little bit about a key point of background. So all of these tools that we have in C, mutexes, barriers, semaphores, they're all built on top of this baseline of atomic operations. Atomic instructions is what the CPU gives us to build concurrency primitives. And so no matter what we're doing to try to have threads communicate and allow them to do that safely without data races, that's going to have to get built on top of atomic operations. And sort of the key one that you want to keep in mind as being a tool that we have is atomic compare and swap. And if we really had to, we could build everything else relatively easily on top of atomic compare and swap. The reason to have other atomic operations is just they might be faster. So that's the plan for today's lecture, and I'm going to come back in a second with a second video where I'll give the first example.